We have Sarah Hormozi here today, and she's from mechanical engineering. And apparently, we're going to play around with cornstarch. It's all yours.
Thank you. Hello, everyone. My name is Sarah Hormozi, and my research group are going to present the behavior and properties of Oobleck, a suspension of cornstarch and water. So I would like to introduce you my research group because you're going to be several stations, and they are going to perform some hands-on experiments for you. So Hussein, Yasaman, who is doing her PhD on cornstarch, Sohrab, Kane, and Muhammad. So some of my group are going to help you, and if you have any questions and you want to experiment something with cornstarch, please ask them. So let's start. So what is it about the physics and future of cornstarch or Oobleck? So first of all, so this is my group. I did the introduction of them. What is Oobleck? Oobleck is a suspension of cornstarch and water. And the term Oobleck was introduced for the first time by Dr. Seuss. So how many people in the audience know him? Okay, everybody. So how many people in the audience are from high school? Good. And how many are from undergrad? I mean, Ohio University people? In science and engineering? Okay, in other discipline? So how many do we have? How many grown-up do we have? So done with the school. Good, great. So everyone, we have a blend of everyone. Okay, great. So Dr. Seuss introduced this Oobleck, and the story is very nice. You can read it in the book that is called Bartholomew and the Oobleck. So the King Erwin is bored with the 4 types of weather that he has in his kingdom. And he calls all of his royal magician to come up with a new thing to fall from the sky. And so that's the news. Oobleck is coming from the sky. And the mission of this young boy is to clear the city from the Oobleck. So let's see how difficult his mission is. To see that, let's prepare some Oobleck and do some experiments with that. So I'm going to pause this for 10 minutes, and we're going to perform some experiments. So you can do it tonight at your home, but don't go to Kroger because we cleared all the cornstarch, so go to Walmart, please. So, and my student Yasama is going to mix it. So basically the recipe is 2 cups of cornstarch and 1 cup of water, because you want it to have it thick, okay? So she's doing it. So if our cameraman could film her, and there are already some prepared Oobleck for you guys on the table. Okay. So the experiment that we want to do, we want to stir Oobleck first. Let's stir it. Let's stir it slowly and fastly. See what happens. So there is no Oobleck here. Okay, perfect. Oh, thank you. Yeah, thanks. Great. So, okay, this is good. So I'm going to do the experiment myself as well. So if I place my hand, it's going to flow inside, okay? And I take it out, and it's flowing. Everything is flowing, yeah? Everything is flowing. So if I stir it slowly, so you can see it, but if I stir it slowly, it looks like fluid. And if I want to do it hard, it's like solid. So it's like I can have sorry, okay, I'm going to clean here. So perhaps I'm going to stay here until the midnight. So I can make a ball of cornstarch in my hand, okay? And if I release the pressure, it's going to flow like a fluid, okay? And it's not dangerous, okay? So try to do that. So, okay, see if Yasaman can make some nice ball, like meatball. and then it flows. As soon as you release the pressure, it's going to flow. And we make it, more fun by just adding some food ink into the Oobleck. Okay, that's why our Oobleck is. Yeah, let's slab it. So if you slab it, okay, it's like solid. It's like you're slabbing a concrete. But if you don't do that, you can just sink your hand into that. So this is, yes. So 2 cups of cornstarch and 1 cup of water. You get Oobleck. Should be thick. So, okay. So if I stir it, it's like a liquid. If I stir it slowly, it's like a liquid. If I do it fast, it's like a solid. Okay, a material which can be both solid and liquid at the same time, depending on how you impose shear on that, right? Can we jump on it? Can we do something more interesting? You cannot walk on the water, right? You're not Jesus, okay? So, but we should find something else to be able to do that. Let's make a pool of that. We made a pool, a small pool of Oobleck over there, and one of my students is going to jump on that cane. Okay, so if he does it fast enough, he's not going to sink. But if he doesn't do it fast enough, he's going to sink. So first attempt was a failure, so that happens. Okay, now I think you need to do a PhD on cornstarch to be able to jump on that. So Yasaman, can you do that? Okay. Yes, good job. She's the Marie Curie of my lab. So now if you stand on that and you don't slap it hard, you're going to sink. Anyone in the audience who wants to try it? Who is, oh, that's a good one. Okay, please. Okay, great. So we have a brave gentleman to try it. Thank you. Yeah, okay, that's great. Oh my goodness, this is a good job. Good job. So a fluid can support weight of a person. That's interesting. That's like a magic mod, if you wish. Good job. So how many people in the audience haven't touched the Oobleck here yet? Okay, you should. Please, don't miss this opportunity. Come here, take it. So 2 cups of cornstarch and 1 cup of water is the recipe. Yes. Oh, that's a good question. I'm going to talk about it, okay? So let's first experiment with that. So the science comes soon. So we could jump on the Oobleck. That's another experiment that we performed here. So now, let's go to the next step. Let's do another fun experiment with Oobleck. We're going to put Oobleck on a speaker. Okay? Let's see how Oobleck dances for us. Okay? Now, we have a speaker here. And then we dyed our Oobleck because we wanted it to be fun. And now we turn on this speaker. So maybe. Come close and watch it if you want, please. It's gonna dance. Too much, huh? Okay. No, you have to take it. Okay, great. Maybe more?
It's a stupid question. You have a question.
Yes.
Does it dance differently via classical or pop?
Yeah, I think so. Yeah. It strongly depends on the beating, and it needs a lot of bass, you know? Yeah, exactly. So how many people want to see it? I mean, if it's not very obvious, so please. That's what I'm here for. Please, we're gonna play this song for the next 1 minute, so please come over and watch it. You guys want to watch it? You should go and watch it. That's beautiful. Please go ahead and watch it. It's once in your lifetime. Just go and watch it. So, great. That's what we do in the lab. So if you want to join my lab, you're going to have lots of fun, okay? So we did a few experiments with the Oobleck. So what is the conclusion? Can I conclude the Oobleck thickens when we shear it? Okay, it thickens when we shear it. And in fluid mechanics, it's a non-Newtonian fluid, and it's been called a shear thickening fluid. And I think that makes total sense, right? If you shear it hard, doesn't matter if you just do it by your hand and with a spoon or whatever else, you shear it hard, it's going to go solid. If you do it slowly and if you shear it slowly, it's going to act like a fluid. That's a very strange behavior. And is it just Oobleck that behaves like that? And the answer is no. We have other materials. Most of the suspensions behave like that, and also debris, for example, in mudslide, landslide, or concrete, an example that you're familiar with. So concrete is a paste of cement and particles, and it acts like that. And when shear thickening, or when this Oobleck property or behavior is bad, so in concrete, as like Oobleck, suppose that you want to construct this huge building. What you have to do, you have to pump lots of concrete into this, basically, to be able to build this building. And when you want to pump hard, the faster you pump, the more difficult it gets, right? Because you know that. You work with Oobleck, right? The faster you want to steer it, it's going to be solid. It's not possible to pump it. So it's a huge loss in concrete industries. And people in concrete industry, they don't like it. They hate it, okay? They want to kill it. But there are some occasions that shear thickening is good. Suppose that you wear a dress made out of Oobleck, okay? So you can walk with that, and you can do whatever you want slowly. And if you go to a war, in army, if the bullet comes, the impact would be a solid impact, not a fluid impact, because the velocity of the bullet is so high, so it's going to hit a solid structure. So in army, in soft body armor, that would be a good application of shear thickening. And the question is that, have people ever thought of that? Thought of using Oobleck in the body armor? And the answer is yes. So scientists in University of Delaware, and okay, now I hope that still works, okay. They used this material. What they did, they soaked this fabric for the body armor into the shear thickening material, not necessarily Oobleck, another kind of shear thickening material. And this is the result. So when the bullet comes, and with the velocity of 250 meters per second, it's very huge. If the fabric is not soaked in the shear thickening material, it would be something like that. However, if you soak it in a shear thickening material, and if you have some layers of this Oobleck, let's say Oobleck material in between, this is going to be the result. So if you look here, if I have some Oobleck or shear thickening material, there is no stretch in the fabric. It resists better. But here, I mean, there is some stretch, but still the bullet could penetrate into the fabric. So, and it makes it useless, yeah? We have to fix it. So can we enhance this shear thickening property to a level that it can resist the bullet, okay? And that's the question that we want to answer. So here, we love shear thickening, and we want to enhance it to be able to apply to army. So the question that a scientist should ask here is, first, how I can control this shear thickening behavior, okay? But before answering this question, one should answer the other question. What is the origin of this shear thickening behavior? So if I don't know what is the origin, that would be very difficult to be able to control it, right? So, so I'm going to give you a couple of solutions for that, okay? So let's look at the Oobleck under microscope. Let's see what is it, okay? So Oobleck was water and cornstarch. If I look at it under microscope, you can see this is water, and these are the grains of cornstarch that are suspended in the water. So what we can see here, so first of all, the grains are not spherical, right? The shape is random. The size is not unique, okay? So you have polydispersity, and if you measure that, the size of cornstarch varies between 5 to 20 micron. What does that mean? It means that in 1 inch, you can have 2,000 grains of cornstarch. That's how small. Okay? And thanks to Dr. Tees, who provided us his microscope to be able to watch it under microscope. And so this is Oobleck. So what is it? It's particles in water, particles in fluid. So the next question that you should ask, if I'm dealing with a system of particle and fluid, what are the forces? What are the main forces in the Oobleck? Okay? And there are so many forces, but there are 3 of those that are dominant. And I'm going to explain those. And most of you know all of these forces: friction, repulsion, and lubrication. So friction and repulsion are forces due to solid-solid contact or solid-solid phase, and lubrication is a solid fluid force. Now, let's introduce them first before going any further. Friction. Suppose that you pile lots of grain. If you pile lots of grain, each grain has a weight, right? So it pushes on the grain beneath it, right? So if you push something, you have to get friction, right? So friction is a long-standing problem. There's so many people have started working on that, from Da Vinci to Klum. And there's a nice, basically, work with Da Vinci. I love this sketch. I love Da Vinci's sketches, but this one is interesting. What he does, he's having like different boxes with the same weight, but he puts them on the table, and he tries at different orientation, and he tries to pull them to see if friction changes or not. Because he didn't know basically what is the relationship between this normal force and basically the tangential force that is friction. That's the answer. You know that it's the same, right? Doesn't matter how you put it on the table. So friction is present whenever you have solid contact. Yes. Can I take the questions after the talk, or if you can wait?
We prefer that you take the questions during, because
Okay. Okay. So because I want to get to the end of my presentation, so go ahead.
So how do these properties vary with temperature and pressure?
Okay. So it might change, but it's a little bit changed. So it's not that significant, but it's not the focus of my talk now. So let me move on, and we can discuss that. But I mean, the friction coefficient doesn't vary with temperature, because the point is that when you have friction in a very tiny surface, you go to plastic regime of solid contact, right? So that doesn't matter if you change temperature anymore. Another force is repulsive force. So when you add solid into a polar solvent, because you're adding cornstarch grains into water, some charges are developed at the surface of the particle. And it can be due to many things, right? Because of the accumulation of electrons. Or if I have a physicist in the room, perhaps they know much more better than me. But the point is that if you have these particles, you have this charged layer around them, electrical double layer they are called, around these particles, and you're fine. And you're fine when these particles are separate from each other. But the problem arises when you want to make them, when you want to bring them to contact, okay? If you want to bring them to contact, you have to overcome this repulsion force, okay? So that's another force, so force number 3. Another one is the lubrication force. So the easiest way for me to explain this force without any equation would be the example of journal bearing. So in journal bearing, what you have a shaft that is rotating in a bearing, right? And all you want to do is to kill the solid contact, because if the rotating shaft has a contact with the bearing, then you would have corrosion, you would have lots of problems, and you don't want that. What they do, they pump a little bit of thin film of fluid between the shaft and the bearing, and what does it fluid do? It just builds up huge pressure, and that huge pressure can basically support the weight of this shaft, okay? And that's basically the way that it can rotate, and it never touches the bearing, okay? Now, why I am introducing that? Because you're adding, to make Oobleck, you're adding these grains of cornstarch into water. So if these are my cornstarch in the water, there is always a thin film of water between these grains, right? The same as this journal bearing problem. So you would expect to have some pressure to be built up between these grains, okay? So this is the third force. So so now I have an assembly of cornstarch and water, and I know that there are three main forces that are playing roles here: friction, repulsion, and lubrication, okay? Now, what is it? What is it coming from, this shear thickening? There is a group of scientists that they believe that shear thickening is coming from the hydroclusters, and lubrication forces are responsible for making those hydroclusters in the suspension. So what does that mean? Let me clarify it for you. So this is Norm Wagner and John Brady from Delaware and Caltech. They're working on this topic for so many years. So this is the reason. They say that suppose that you have your cornstarch in water, okay, and you start shearing it. When you start shearing it, as you shear it faster and faster, like you're steering it faster and faster, what happens, grains of cornstarch come close to each other, okay? When they come close to each other, a film of water is forming between them, right? They are making that lubrication force that they never touch, but they never can escape from that. And the reason is that if you have two smooth surface, you know, like glass, and you want to attach them, it's very difficult to do so. You should apply lots of energy. So what happens, you do that, you shear the suspension, the particles, the grains of cornstarch come into contact, lubrication force basically fixes them together. You get these clusters of particles that are attached together and they want to move. As you shear faster, you have to shear these large clusters. And this is really difficult to do. That's why when you want to shear faster and faster the Oobleck, it can't go, because you are shearing these large particles. You want these large clusters to move, okay? So this is one theory, okay? The other one, some group of scientists, they think that lubrication force does nothing. It's all about friction and repulsion. So what they say, so there are people that I have written their names here, what they say is the following. They say that suppose that you have 2 grains of cornstarch in water and you shear them, right? Nothing happens. But suppose that you shear them fast. If you want to make a contact, you have to overcome this repulsion force. And if you could do that, what happens? They come to contact, now friction is playing the role. And you know friction is really a strong force. So they did a very nice simulation. What they did, they put this assembly of particles in the water, in the assembly of grains in water or a fluid, and they apply shear on that. And they basically, these chains that these lines or rods that you're looking at is when you have a contact, okay? So when you have a friction, when you have a contact between the grains and you have a frictional chain, frictional force, let's say. So when shear is small, when you steer slowly, there are few contacts, there are few frictional chains in the Oobleck. But as you do it fast, as you shear it hard, you overcome more and more of this repulsion force, and you bring the contact lots of particles, okay? So you can see that there's so many frictional forces chains here now. So it's really difficult to move or make an assembly of solid chains to move. That's what happens, they say. Thank you. Is it good? Okay, thank you. So this is another another group of scientists, okay, the third group of scientists, they say that shear thickening is more than this. It's more complex than this. They could do experiments that violate all of these assumptions, and to date, there is no single experiment that can explain this behavior. So what they did a nice experiment, and they put this Oobleck into this annulus. So you have two cylinders. The inner cylinder is rotating, and what happens, they see that, so this is the density of the grains. So the grains are homogeneously distributed across this annulus, and they start to rotate. As they start to rotate, they see that in a very fast time scale, the grains migrate toward the outer cylinder. And you know that when it happens, so suppose that I give you a cube, and I ask you fill it with particles. You cannot fill it with a certain number of, more than a certain number of particles, right? Because of the geometry constraint. So that's what they say. They say that these grains migrate, and they go to the region, and that region cannot have more than this number of grains, and the whole system jams. It's like solid. That's what you get. And they think that lubrication, friction, repulsion, everything is there, and more than that, there are the constraints that we have from geometry. Okay, if I confine something, an assembly of grain and fluid, and I want to basically shear that, particles have to go around each other, have to move around each other, and it should dilate the system. When you confine the system, so the system doesn't have any choice except jamming. Okay, so that's the other group of scientists, and some people say that, okay, this is wrong to say just lubrication force, how about inertia? Okay, so the conclusion is that what is the origin of shear thickening behavior? Still an open question. Okay, and there are so many people like Yasaman who is doing PhD on this topic. But, okay, we are an engineer, I am an engineer, and I really don't care that physicists are fighting with each other. I want to apply it to a cool problem, right? So now, okay, I want to solve this soft body armor problem. I showed you that I don't have enough shear thickening in my fabric to prevent the bullet. The question is that, can I enhance that shear thickening? This is what we did. What we did, this is Yasaman's PhD. So what she did basically, she loaded some Oobleck between these two plates, okay? And she started to shear that. So, and she is increasing the velocity or the rotating speed of the top plate. And there is a spring on top that it measures the torque. So what is the torque? It's the resistance to the rotation that you apply to this Oobleck. So what she does, she's recording this torque, and she says that as she increases the speed, the torque or resistance increases. No wonder. You did this experiment with your hand, right? You were steering it slowly, and then you wanted to do it fast. It was more difficult. And at some point, at certain speed of steering, boom, you have this jump. Everything is solid. The torque basically diverges, right? So this is what happens with the Oobleck. But we know this is not enough because it cannot still prevent the bullet, right? The point is that, can I enhance it? This is what she did. She said, now, let's add some large particles to this Oobleck, okay, and do the experiment again. Let's see if I add large particles to the Oobleck, I can enhance the shear thickening. Let's do the experiment again. Now she's loading this sample between these two plates, rotating the top plate, measuring the torque. There we go. We get this jump in the torque at way smaller speed, okay? Means that we enhance the shear thickening with like tens of order. Well, what is happening? Why these grains, these large particles are helping me to enhance the shear thickening? I have a cartoon for you. Suppose that you have this oobleck here, okay? You add large particles to that. So what happens? You start to shear it. You start to rotate the top plate. So the oobleck wants to flow, right? So it's flowing until it sees the particles. Now, with the same velocity, it should go through these particles, between these particles. So you're constraining the area, but mass is concerned. What is the solution? You have to go faster, right? What we do, we are increasing the speed and shear locally between the grains. And what happens? You know that. If you do that, the oobleck is going to be solid, right? So that's what she did, and that's what we have to submit. And can we fix this? Hopefully we can. Let's try it. Let's do the last experiment here. What we want to do here, she has some oobleck that is rotating, and I think the thickness of this oobleck is much less than what we did the experiment with. So even we can do it when your oobleck is not shear thickened. And we add particles to it, and then 10, 20 times larger than the grains of cornstarch. We add it. If you don't believe us, please come and try it. Polyester particles, they are, and they can be anything. We tried it with PMM plexiglass particles. We tried it with glass particles, with silver-coated plexiglass particles. We did it with everything, and it worked. Okay? Okay. She was able to steer it before. Adding a little bit of large particles enhances the shear thickening a lot. Okay? Now, okay, I think that was the last experiment. So I want to acknowledge my colleagues here and NSF for supporting us, and the ANR of France. Also, I want to acknowledge Dr. Tees, who kindly, gave us the permission of using his set of microscopes, and my group, who are always there for me. And I want to thank a couple of more people. Adra Hadi, she's there. She's helping me with all of this research manuscript that I write and send to NSF. So she's fantastic in terms of reading my boring scientific drafts. And I want to thank those people who introduced this wonderful topic to me. Bloen Metzger, Olivier Poulican, Yoel Forte, Guillaume Oberles, and Elizabeth Guzali. And thank you so much for being here and for listening to me. Now I would...
We're open for questions, guys. So with the body armor application, since body armor is in like a vertical orientation when you're wearing it, what prevents over time if the oobleck from flowing down and collecting?
You can make a density match, right? Because okay, so the question is that if I make the oobleck and wear it, so perhaps the grains of cornstarch are heavier than water and they sediment, right? Is this question how I can prevent the sedimentation?
Not just that they're heavier than water, but just that like it's going to collect here, not just along your body, because when it's not being sheared, it's liquid, right?
Right. I think, yeah, the point is that gravity just plays a role when you have a density difference. So if I have a solid that is heavier than my environment fluid, it's going to settle. Or if it's lighter, it's going to rise up, right? But if I have the fluid as the exact same density as my solid, it's going to stay there, okay? And that's why Yasaman is doing. All of the experiments that we are performing are in a density match situation, meaning that if you leave oobleck, it's not going to accumulate in the bottom or in the top. So it's going to stay there because there's nothing to act on that.
So if you go back to your slides, like there was a graph, if I understood that correctly, any one of those, the next one. So on the horizontal axis is the speed, and on the vertical, a kind of
It's a torque.
resistance,
Yes,
right?
yeah.
So my understanding is like to a certain speed, it goes smooth, slower speeds. When it moves to a certain high speed, then the force required to somehow is increasing, right?
Right.
So now, how can that force be reduced? Or like you probably mentioned about that as well. And so for the bullet and for other particles that you mentioned, is there any other particle like other than starch that can be used for this? And how can that force be? Is that force a good force?
Okay.
Basically,
Okay, yeah. I think the question is, first of all, if there is an enhancement in torque or the force, how we can decrease that. And the second question is that, is there any other particles that we can have that behaves like cornstarch in water? So I'm going to answer the second question first. So yes, there are. There's some, you can charge silica particles, for example, and add it to a liquid, and they go shear thicken. So there's tons of that. Okay, so this is the problem that this is basically shear thickening behavior exists for so many colloidal suspensions and non-colloidal suspensions. So the answer to your second question. And the first question, the point is that there are two, so if I didn't go into detail, and to be honest, it's perhaps the first presentation of my mind without a single equation in that. So my students from mathematics course know that. There are two types of shear thickening behavior: the continuous shear thickening behavior and discontinuous shear thickening behavior. What I'm presenting here is discontinuous shear thickening behavior. Then when you get to this regime, that meaning that the volume fraction of solid is high in your system, you get this huge jump, okay? And now how you can reduce that, you have to reduce the volume fraction of solid in your water, or the volume fraction of the cornstarch in your water, to go to continuous shear thickening, which is a kind of slight increase in the torque. It's not discontinuous like that.
so just to follow up on that, if we keep increasing the speed, do we see breaks like that?
No, because at this point, what happens, the whole oobleck is going to go solid, and it just attaches and it comes out of your geometry configuration, you know? Yes?
So my question is, you said that you kind of indicated that the different sizes of the cornstarch particle is what helps it with is the different sizes kind of what helps with the shear thickening, right?
That's a very good question. So yeah.
Why did you use particles that are 10 times larger? Why did you try like a variety of sizes? Why did you decide to use that?
Yeah, okay, that's a tricky question. Okay, it's a good one. Okay, so the question is that why did I choose particles that are way larger than the cornstarch grain, right? So we would love to solve the equations, right? So the point is that I wanted my particles to see the oobleck as a continuum fluid. Okay? So you're working with a discrete system of particles and water, small particles and water, but on the scale of these large particles, I want to see something uniform. If I want to have that, I have to have particles that are way larger than the cornstarch grain. Okay, that's the answer to your question. But having said that, if we add smaller particles, we showed that we can enhance shear thickening even more. Yes. So polydispersity definitely helps here. Right. Very good question.
So, with the bullet technique, does that happen because like there is a limit of how much force you can apply? Like if you apply more pressure, then that threshold you can overcome the shear thickening.
Yeah, I think the question is that why it does penetrate into the sample, and if there is a characteristic force that beyond that you're going to destroy the thickening behavior. So that's a very nice question, because of course bullet can penetrate into lots of solids, right? So when you basically destroy the structure of solid, yeah, I mean, it happens, right? So that there is a point always. But the point is that, the whole point is that, can I enhance that structure in a good way, the property of that structure, solid structure, in a good way, to be able to resist the force of the impact.
So, like, if that is possible, it's also possible to develop a bullet that
Oh, that's true. Oh, that's a good one. Thank you. Another application maybe for Yasaman to work on. Okay. So which one we're going to take? The question is that, can we use other fluids than water to make Oobleck? Yes, you can, but the point is that this polar solvent is very important, perhaps due to that repulsion friction theory that I told you, and you want to have that electrical double layer. So with Yasaman, we tried to solve Oobleck in polyethylene glycol, and it didn't work. So it doesn't have that property. So it matters. Yeah, chemistry of surface matters. So I'm not sure if I understand the question very well. So is it like you want to know, if you get to that certain speed, that the Oobleck goes to solid phase, if it gets the certain shape or something? That's the question? No, it's a very unstable system actually. You know, the drops of Oobleck comes out of the plate, and it can be any shape. You know, because people from physics, again, can help it. It's a statistical problem, right? So there is, the system is, you shear it, there's so many particles, so each time that you do that, there's no certain way to come up with the same configuration as before. See? Yes?
Why not use something more viscous like oil instead of water?
Yeah, that was the question. Yes, that was, if we can do it with any other fluid, we can, but we can perhaps do it with oil. But the point is that you have to, there should be a certain oil, I would say.
Can I ask a second question then real quick? Did you use a gun in the lab?
No, actually we didn't do that. No, that's a fun experiment to do. My lab is not, I have a small lab. I have to. Exactly.
So I've heard of an application in body armor using a fluid called magnetoreological fluid,
Uh-huh.
which I think might be the same as Oobleck. So my question really is, which one is more advantageous, Oobleck or magnetoreological fluid?
That's a very good question. There are some magnet fluids that they are used in the army application to make the soft body armor. And the point is that what they do, they apply the electric field and they polarize this fluid. And when they do that, there are basically the molecules of fluid or the structure of fluids kind of arrange itself in a certain way, like making chains. Okay, the